Welcome to this session. In this lecture, we will begin our journey with one of the most important and widely used programming languages in the field of machine learning, artificial intelligence, and data science, and that's Python. So let's get started. Before focus on Python, it is important for us to appreciate the broader landscape of tools that are commonly used in data science today. For data pre-processing and analysis, the first and most critical step in any data science workflow, we have tools like Python, R, Microsoft Excel, SAS, and SPSS. Each of these has its own strengths. SAS and SPSS, for example, are widely used in clinical and social science research. Excel remains relevant for quick business analysis. However, Python and R dominate in academic and industry data science roles. For data exploration and visualization, tools like Tableau and Power BI allow us to build interactive dashboards and communicate insights effectively to non technical audiences. When the volume of data grows very large, what we call big data, we move to distributed computing frameworks like Apache Spark and Apache Hadoop, which allow us to process data across multiple machines in parallel. And in the most recent developments, we have a rapidly growing category, generative AI and large language model development supported by frameworks like LangChain, Hugging Face, and the OpenAI API. Now we will notice that Python is relevant across almost all of these categories. That's precisely why we are starting here. Let's understand where Python comes from and how it has evolved over the decades. Python was created by Guido van Rossum in the late 1980s while he was working at the National Research Institute for Mathematics and Computer Science in the Netherlands. His goal was to design a language that was easy to read, easy to write, and powerful enough for real world use. Python 1.0 was the first official release, a working functional language, but one that would evolve significantly. Python 2.0 introduced many important improvements, but it reached its official end of life in January 2020 and is no longer supported. Python 3.0 was a major milestone. It resolved many fundamental design issues in the language, and all modern development uses Python 3. The latest stable version is Python 3.14, released in October 2025. Python continues to be actively developed, and each version brings improvements in performance, security, and language features. I encourage you to always use the latest stable release. Now, let's look at some of the core technical characteristics of Python. Understanding these will help you write better code and debug problems more effectively. The first feature is multi-paradigm support. Python supports three major programming paradigms: functional programming, structural or procedural programming, and object-oriented programming, commonly abbreviated as OOPS. In data science, we regularly use all three styles within the same project. For example, data transformations are often written in a functional style, while building ML pipelines or custom models uses OOPS. The second feature is dynamic typing. In Python, you do not need to declare the type of a variable before using it. The type is determined automatically at runtime. For instance, you can write x is equal to 10 and Python knows x is an integer. This makes coding faster and more flexible, but it also means you need to be careful in production systems. A type mismatch caught late can cause significant issues. This is why we use tools like type hints and unit testing in professional workflows. Third is reference counting, Python's primary mechanism for memory management. Every object in Python has a reference count. When no variable is pointing to an object, Python automatically deallocates it from memory. As a data scientist, this matters when you're working with large data sets in memory. Understanding how Python manages objects helps you avoid memory overflows. Fourth is late binding. In Python, method and variable names are resolved at runtime, not at the time of writing the code. This enables Python's highly dynamic and flexible behavior. It is one reason why libraries like scikit-learn and TensorFlow can offer such expressive and extensible APIs. Finally, Python's entire design philosophy is captured in the Zen of Python by Tim Peters, 20 guiding aphorisms worth reading. Simply run input this in any Python environment to see them. Let us now look at Python from a broader perspective, its governance, strengths, and the ecosystem around it. Python is maintained by the Python Software Foundation, a non-profit organization that oversees the development of the language. The standard implementation of Python, called CPython, is written in the C programming language. This is the version most of us install and use. In terms of language strength, Python is known for three things in particular. First, high readability. Python code reads almost like plain English, which significantly reduces the learning curve and makes collaboration easier. Second, excellent error handling. Python's exceptional handling system is clean and expressive. Third, a large and active community. There are millions of Python developers worldwide, which means abundant documentation, tutorials, packages, and support forums. Beyond C Python, there are several alternative Python interpreters worth knowing about. JPython for the Java ecosystem, IronPython for .NET, Stackless Python for high concurrency applications, and PyPy, which uses just-in-time compilation for notable speed gains in non-vectorized code. Finally, Python is cross-platform. It runs on Windows, Linux, and Mac OS with no changes to your code. This is extremely important in a course context where learners may be using different operating systems. This slide summarizes why Python has become the standard language for machine learning, AI, and data science. Let's go through each advantage carefully. First, it is open source. Python is developed under the Open Source Initiative license. This means it is completely free to use, modify, and distribute, even for commercial purposes. There is no licensing fee, no vendor lock in. This has been a major driver of its global adoption, particularly in academic and research communities. Second, simple and readable syntax. Python's syntax is clean and closer to natural language than many other languages. When you write Python code, it is easy for your team members to read and review it. In a data science team, where codes needs to be shared, peer reviewed, and handed over, readability is a significant practical advantage. Third, a rich ecosystem of data science libraries. This is perhaps the most important reason for Python's dominance in our field. Libraries like NumPy for numerical computing, Pandas for data manipulation, Matplotlib for visualization, scikit-learn for classical machine learning, and TensorFlow and PyTorch for deep learning. These are industry standard production grade tools maintained by thousands of contributors worldwide. You will use most of these in this course. Fourth, integration with cloud platforms. Python integrates seamlessly with all major cloud services: AWS, Microsoft Azure, Google Cloud, and platforms like Databricks. This makes Python the natural choice for building scalable cloud native data pipelines and deploying ML models in production. These four reasons together explain why Python is the language of choice in virtually every top data science and AI team in the world today. Now let's turn to a practical question. How do we actually write and run Python code? At its most basic level, a Python program is a text file saved with the extension .py executed from the command line or terminal. However, for learning and data science work, we use an IDE or integrated development environment, which brings together a code editor, interpreter, debugger, and more in a single interface. Two resources worth bookmarking right away: the official Python download at python.org and the full documentation at docs.python.org. These will be your most reliable references throughout this course.
Let's understand what an IDE is and why it matters. An IDE, Integrated Development Environment, combines all the tools a programmer needs into one unified interface: a source code editor, a compiler or interpreter, and a debugger. Modern IDEs also offer syntax highlighting, real time error detection, and intelligent code completion, features that significantly reduce errors and speed up development. The result is a streamlined workflow where you can write, run, debug, and deploy code without ever leaving the application. There are many IDEs available for Python development. Popular choices include Visual Studio Code, PyCharm, and Vim. Each has its strengths, and experienced developers often have strong preferences. In this course, we will primarily work with three environments, each suited to different stages of the learning and development process. Google Colab is a cloud based notebook environment that requires no installation whatsoever. You need only a Google account and a web browser. All computation happens on Google servers. This is ideal for beginners, for quick experimentation, and for sharing your work with others. Simply share a link. Jupyter Notebook is the interactive cell based notebook environment that has become a standard tool in data science. It allows you to write code, run it incrementally, see the output in line, and document your analysis with text and equations, all in a single document. We will use this extensively throughout the course. Spider is an IDE specifically designed for scientific computing and data science. It offers a MATLAB like interface with a code editor, variable explorer, and interactive console, making it particularly well suited for learners with a scientific or engineering background. Spider, which stands for Scientific Python Development Environment, is one of the most recommended IDEs for learners transitioning into data science, particularly those coming from MATLAB or R background. Spider is a cross platform. It runs on Windows, Linux, and Mac OS. It is open source and freely available. The easiest way to install it is through the Anaconda distribution, which we will discuss shortly. Anaconda bundles Python, Spider, Jupyter Notebook, and all the major data science libraries in a single installation, which greatly simplifies setup. The key features of Spider include a code editor with syntax highlighting and real time error detection, which helps you catch mistakes immediately, code completion and navigation, which speeds up development, a built in debugger, and integrated documentation. You can read the documentation of any function directly within the IDE without switching to a browser. This slide shows the actual Spider interface. Let's take a moment to orient ourselves. On the left side, you have the code editor. This is where you write your Python scripts. On the upper right, you will see the variable explorer. This is an incredibly useful feature. It shows all the variables currently in memory along with their types and values. When you are working with data frames and arrays, being able to inspect them visually without writing print statement is a major productivity advantage. On the lower right is the IPython console. This is where your code runs and outputs are displayed. You can also type and run commands here interactively. I encourage you to open Spider on your own machine after this lecture, explore the interface, and try running a few simple commands. Familiarity with the environment will make the coding session much smoother. Jupyter Notebook is a web based interactive computing environment that allows you to create documents called notebooks that combine live Python code, its output, visualizations, and written explanations in a single file. Jupyter is cross platform, open source, and available through Anaconda or as a standalone install. An important point worth noting: Jupyter is not Python specific. The name Jupyter is actually derived from three languages. It originally supported Julia, Python, and R. It also supports Scala. However, Python is by far the most common language used with Jupyter, and all our exercises will be in Python. A Jupyter notebook is structured as an ordered sequence of cells. Each cell can contain either code, which you run and see the output of immediately, or Markdown text, which allows you to write formatted explanations, equations, and headings. This cell by cell execution model is what makes Jupyter so powerful for data exploration. You can run one step, inspect the output, and decide what to do next without rerunning your entire program. This is also why Jupyter Notebook have become the standard format for sharing data science work. A notebook can serve simultaneously a code, documentation, and analysis report. As we wrap up this session, let's address a practical question you may have. With all these options available, which IDE should you use? The answer depends on your use case, stage of work, and honestly, the best way to develop a preference is simply to use different environments and observe what suits your workflow. Here is a quick guide to help you decide. If you are learning Python or doing early stage exploratory data analysis, start with Google Colab or Jupyter Notebook. They require minimal setup, run in your browser, and allow you to focus entirely on the code rather than the environment. If you're working on full data science projects with multiple scripts, version control, and production ready code, Visual Studio Code is the industry standard. Its extensions for Python, Git integration, and remote development capabilities make it highly versatile. For large scale enterprise Python applications, complex multi module code bases with many developers, PyCharm provides deeper code analysis, refactoring tools, and project management features. And if your background is in scientific computing and you prefer a MATLAB like experience with a variable explorer and integrated console, Spider is your best choice.
In this course, we will primarily use Google Colab, Jupyter Notebook, and Spider. As you grow as practitioner, VS Code and PyCharm are worth exploring for larger projects. That brings us to the end of this introductory lecture on Python. In the next session, we will begin working directly in Python, setting up our environment and writing our first programs. Thank you.